Hello. This time we're going to explore a fundamental relation in trees. And is that associated with the number of vertices and the number of edges? So, what we're going to do is at the end of this video, you will learn that the number of edges and the number of vertices in a tree differ only by one. We're going to only use elementary techniques. So I'll start with a few definitions. First, what is a maximal path? So a maximal path, of course, simple path, is a path that is not properly contained in any other. So for this, I'm going to provide an example for this. Suppose that I have the following graph. And I label this as 1, 2, 3, 4, and 5. And this one is 6. Why not? Then look, the path associated with 1, 6, 4, and then 5 is maximal. While the path, let's say going from 6 then to 4 is not, because that one is contained in this one, for example, right? For the same reason, right? The path 2, 6, 3 is maximal, but the path 2, 6 is not, as we can see that this path is contained in this one. Okay, so based on this idea, we have the following observation. A maximal path in a tree with at least 2 vertices cannot be, right? It cannot be a single vertex, of course. Right? The path cannot consist of only one vertex. Why? Well, we have at least 2 vertices, and a tree is connected, so there should be, well, one path joining those two. And that path should be contained in another maximal path. And it cannot be a cycle. Why? Well, because a tree is a connected, a cyclic graph, right? So this maximal path cannot be a cycle. Okay. So what is the observation that follows from this? Well, so the initial and terminal vertices in such a path must be of degree 1. Why? Because this first observation that associated with A excludes the possibility that the degree is 0. And the second observation excludes the possibility that the degree is 2. So this is really the only thing that can happen. Okay, so now, ready for the next part? 3. Well, let T be a tree with at least 2 vertices. So we have exactly the same conditions as the ones that are associated with the second point. What we're going to do is the following. Let W be one of the vertices of t of degree 1. There should be at least one of such vertices. Why? Because there's at least one maximal path, right? And in that maximal path, there are at least, well, two vertices of degree 1, right? The terminal and the initial one. So, what is it we're going to do now? Well, from here, we're going to take away that vertex. So the observation is the following. We select that vertex of degree 1 in the tree. The process of removing it, along with its edges, produces another tree. Look, in the graph that we have above, in number 1, we observe that this one that I'm circling here has degree 1. Now, if I was to remove it, along with its incident edge, which is the only one that it has, what remains is a structure, which is a graph, that is also a tree. So what we're going to do here is to prove it in the general case, right? That we can always perform such an operation. So we'll start like this. So the first thing is that we can see that T prime is acyclic. Why is that? Well, because it's a subgraph of an already acyclic graph, right? So it should not contain cycles. Otherwise, you would be violating the condition that the original graph has no cycles. Right? And T prime is a subgraph of T. Now, from here, we're going to do the following. Let U and V be in T prime. The only thing that remains for us to demonstrate is that T prime is connected for T prime to be a tree. So, and let P be a path, of course, in T from U to V, right? The existence of this path is guaranteed from the assumption that T is a tree, because that is connected. Okay, so what is that we can say? Well, clearly, we have that U and V are different from W, right? Because that is the vertex that we removed. So we'll continue with this. What I'm going to do now is to exemplify what or expand the path, right, in its full form. So I read the path as U0, E1, U1, then followed by E2, then followed by U2, then we'll continue with this, En, Un. Of course, what I'm indicating here is that I start at vertex U0, I end at vertex Un, and I follow the edge that I labeled as E1 while moving from U0 to U1. I follow the edge E2 while moving from U1 to U2, and so on and so on. So, in this case, we have that U0 is U, and Un is V, as I'm traveling from U to V. Now, what we can observe is that each internal vertex in this path has degree at least 2. Well, why is that? Well, imagine the ones that are internal, right? Let's take, for example, this. And the same argument goes for both. Well, this one, right, we have 2 incident edges. The one that is associated here and the one that is associated here. Of course, we're making the assumption that we're taking a simple path, right, for simplification, so that we don't have repetitions. Well, what is it we get from here? Well, then, for each I in the range from 1 up to n minus 1, we have that ui is different from w. And why is that? Well, because their degrees do not match, right? The degrees of the internal vertices are all different from the one associated with w, which is that of 1. Okay, well, this demonstrates that the path that we are describing here, so P is a path in T prime from U to V. Hence, T prime is connected. But since it's a cyclic, it is also a tree. So to finish with the demonstration here, what we're going to show, the final thing, the one that we care the most, is that every tree with n vertices has n minus 1 edges. So the proof will proceed by induction on the number of vertices. So we'll go like this. If n is equal to 1, well, then the tree that we're considering is only one vertex. And no edges. We're done, right? One vertex, no edges. Now, let k, for the inductive step, be greater or equal to 1. And suppose that every tree with k vertices has, k minus 1 edges. What we're going to do is use the following. Let T be a tree with k plus 1 vertices. Well, then k plus 1 is greater or equal than 2, right? That means that T has at least 2 vertices. Right? That means that we can use the results that is associated with this. We may construct this T prime. Okay, well, let's do it. Then T has a vertex of degree 1. Let T prime be the tree obtained by removing such vertex? Well, then, by hypothesis, T prime has, well, k vertices, and hence k minus 1 edges. Well, imagine that you put it back, right? So T has k plus 1 vertices. And, well, look, all that we're going to do is restore that edge. And with this, we conclude the proof. I hope that you enjoy it. Take care.